Thank you also to everyone who has invited me in this center, the Tushita Center. It's the second time I come, and I always feel moving to be with you.
Is you audible? No?
No. Okay, maybe I should...
Can you hold it?
I can hold it, yes.
It's not a problem?
Yes, okay. Now I'm sure you can hear me, because I hear my voice echoing. Okay. So
the projector is here, so we can do that.
It's already here.
No, they've arrived.
Okay, so maybe the projector will be with us at some time during this conference. So the title that was announced by Renuka was Quantum Physics and Buddhism. Here, I think I've chosen a slightly more specialized issue, because I don't wish to speak for 2 hours. But my real title is, Do Particles Inherently Exist? And you immediately understand the connection with Buddhism. It's a problem of absence or presence of inherent properties and inherent existence of the bearer of properties. The bearer of properties is the particle. For instance, a particle, an elementary particle, is usually defined by its mass, its charge, electric charge, and several other characteristics. But is there something behind these characteristics that is enduring, that is still there when nobody tries to capture it, and so on? Here are the questions, and I will connect this issue with Buddhism in the course of the exposition. So, to begin with, in order for something to be said to exist, you must have some criteria. When do you say that something exists? And what it is to exist? It's a very difficult question, in fact. But usually, in ordinary life, when you say that something exists, is first of all that you have perceived it, and secondly that you didn't have just a flickering perception. You had a continuous perception and an ability to follow the thing in its history, to retrieve the thing when you come back and see again, and also you need some criteria to be sure that the thing you see one day is the same as the thing you see the other day. When all these criteria are met, you can say the thing exists. Okay, this is a practical definition. It's not an eerie metaphysical definition. Just how do you do in practice in everyday life to say, oh, this table exists, you know? It's because you have seen it yesterday and re-identified it and seen its similarity. So there are, in fact, in the history of philosophy, there has been 3 amazingly different definitions of the of the individuality of the things that are deemed to be existent. The first conception of the individuality of the things that are deemed to exist is precisely intrinsic existence. There is something solid, existent, and then you ascribe to it properties. So why did people think of this strange idea of something that exists even beyond what can be seen of it, even beyond the properties that can be ascribed to it? Where did it come? Very simple. It comes from the language, from the proposition. A proposition has, in any language, virtually, has a grammatical subject and a predicate. For instance, the sky is blue. The subject is the sky, and blue is the predicate. And so, as the philosopher Wittgenstein said once, when there is a substantive, namely a grammatical subject of a proposition, one immediately thinks of a substance, namely of something enduring, permanent, that is able to bear all these properties that are ascribed to it. Okay, so in fact, you see, here it's very important to see that our belief in the inherent existence of these bearers of properties that we call substances comes in fact from a linguistic model. So in fact I would say it's a sort of superimposition, not from a certain concept, but from the general structure of language, which is probably the reason why this belief in the existence of a bearer of properties is so strong and so difficult to unroot. It's because it's really written in the language. But now there are other definitions of the individuality of entities. Another definition is just the collection of its properties, of its characteristics. For instance, you would say, okay, there exists something that is orange, small and spherical. And this is enough to define the thing that we are trying to characterize, because all its characteristics are listed, and in fact, according to this definition, the thing is nothing more and nothing beyond the list of its characteristics. Okay? And this led to a principle that was formulated by the German philosopher of the end of the 17th century, Leibniz. Certainly have heard of Leibniz. This principle is the principle of identity of indiscernible, namely something that has the same properties as something else is in fact the same thing. Instead, in the former definition, you could have something that has the same property as some other things, but since its individuality is contained in the depth of it, it is intrinsically possessed by it, then you can have two things that have exactly the same properties and yet are different. Okay? So these are clearly two very different conceptions of what is a thing. A third possibility is just eliminate these ideas of intrinsic existence or this idea that a thing reduces to the list of its properties, but say that the individuality of something is determined by its position. If you say, what is this table? It is the thing that is at this place. You know, what is this other table? It is the thing that is at a distance d from the first table, and it's at a different position. So here, it is the position that defines the individuality of each thing. Okay, so three definitions, very different. Now, which one will apply to quantum particles? This is the question. But the first one, to begin with, is inapplicable in practice, for the same simple reason that one postulates something that is beyond any capability of observation. It's completely abstract, completely linguistic. So forget it for the time being. The second one is much more plausible, because obviously you can measure a list of characteristics of particles and ascribe a certain individuality to the particles in the name of this list of characteristics. For instance, you will say an electron is a particle with mass, I don't say which mass, but at any rate, a certain mass and a certain electric charge. Is it enough to individualize a particular electron? Obviously not, because all the electrons have the same mass and the same electric charge. So you need something else. What can be this something else? Position. Only the position. Hence, the third definition is much more expedient in quantum physics. The position. You will not say this electron is characterized, this electron is this electron because it is characterized by a list of characteristics. You will say this electron is this electron because it is there at this point. And it's different from this one. Okay. Now, maybe you have heard of something, one of the most important features of quantum physics. It's called the Heisenberg's uncertainty principle. Okay. That means that you cannot know the position and the velocity of something, for instance an electron, to a precision that is major than a certain quantity. This quantity is the Planck constant in quantum mechanics. Okay? So there are limits to your possible knowledge, for instance, of the position of the electron. In this case, let's suppose that two electrons come close together. What happens? You no longer can distinguish between the two electrons. Which is which? You don't know. The identity of the electrons is lost. Okay? So, which one is which one? Then, in this case, things become serious because you have lost one of the major criteria that define an entity in ordinary life. You can no longer identify something. And this criterion is so important that an American philosopher called Quine has coined a sort of slogan about the connection between identity and existence. He said, there is no entity without identity. It's very easy to remember, because there is a rhyme, no entity without identity. Why? Because one of the main criteria for saying it is this entity and not another is lost. So you feel that something has escaped you when the criterion of identity by location in space has been lost. Something very important, in fact. And this is not really new, in fact. The importance of this criterion was already known even in the time of classical physics. And it was so important that particles in classical physics in the 19th century were defined by the possibility of following continuously the trajectory of something. Even more, people withdrew the idea, the notion of that being, and replaced it with the possibility of following a trajectory. Let's read a sentence by Heinrich Hertz. Hertz is well known, in fact. Maybe you have heard of Hertzian waves, or of the frequency of Hertz. For instance, when you think of the frequency of the how do you say that? The processor of a computer, it's formulated in megahertz or something like that. So Hertz was a German physicist who discovered the concept of electromagnetic waves. Okay. So, but he was also a specialist of mechanics, particles, and so on. And he said that a material particle is a function. A material particle is a function by which we associate unambiguously a point of space at a certain time with another point at another time. So it's very interesting as a definition. The particle is no longer here a being with an inherent existence. It's a function by which we associate one point at a certain time with another point at another time. So you see, here you feel that something is progressively disappearing from the thought of the physicist. It's precisely the idea of intrinsic existence. We just have a spot here. We associate this spot with another spot there, and we say, there must be a particle there. We define the particle by this association between two spots, two discontinuous events, two discontinuous phenomena. You feel here, the idea of impermanence that is creeping behind that. Namely, you no longer have this idea that there is something behind the appearances that is permanently existent, and so on. You just have spots, appearances, glitters, and you associate them together, and you say, this must be a particle. Or I define the particle this way. Conversely, when this criterion is not fulfilled, as it is the case in quantum physics for the reason I've told you, namely that the uncertainty principle doesn't enable you to identify permanently every particle. When you cannot do that, when you cannot use this function, precise function, to associate one spot to another spot, then there is doubt. Is there really a particle there? And Erwin Schrödinger, who was one of the creators of quantum physics, wrote the following sentence. What is a particle that has no trajectory or no path? To me, giving up the path means giving up the particle. So, if Hertz's criterion is not fulfilled, physicists become doubtful of the intrinsic existence of particles. One day, I had a friend who is a specialist of particle physics, and he laughed, and he said, I'm a specialist of a discipline whose object doesn't exist. Okay, here there is a slide that is a little bit more complex. And of course, I would have liked to have the picture, but okay, I will try to explain.
He's there?
We can, it will take 5 minutes.
It'll take 5 minutes, it's there.
Yes. Okay.
Can we fix it up?
Maybe I can go on.
Okay.
Because if not, we make a break and. It's
okay, please go on.
So, I think it's important to have this. This idea that I want to expound to you now, because it was invented by an Indian scientist, Satyendra Bose. Is it okay, the pronunciation? Satyendra Bose.
Yeah.
Yes. So he is very well-known scientist. And you know that his main discovery is precisely a criticism of the individuality of particles. It was in the 1920s. He sent a paper to Einstein, and Einstein received the paper from this Indian scientist, and he said, wonderful, that's really a great discovery. I will publish it immediately in a German journal. And Einstein translated himself the paper of Bose from English to German. At that time, German was, one of the main scientific languages. So, what did he understand? What did Bose understand? Is that when you count particles, you count them in such a way that there is a meaning saying that particle A is here and particle B is there. But then there are another possibility is that particle B comes here and particle A comes here. Or there can be A and B here, or A and B there. So there are four cases. But let's suppose you cannot distinguish between these two particles. Let's suppose, because of the uncertainty principle, that it's impossible to distinguish between them. Then there is no sense saying that A and B are there, or A and B are there. The only thing that we can say is two particles are there, or one is here, one is here. But there is no longer any difference between A here and B here, or B here and A here. There is no longer difference. The only relevant case is just one here, one here. Which one we cannot know. There is no sense asking the question. Just this little modification in the counting of the cases of distributions of particles made him invent a major notion of science, the idea that particles can, so to speak, deposit all in the same state. And this became known as Bose condensation. It's used everywhere. For instance, it's used in the case of, superconductivity, superfluidity, and so on and so on. At any rate, that means for us it's not so important. So physical applications are not so important. But that means that there is a signature of the fact that particles have no identity in quantum physics. And this signature is visible in major physical effects. And this has been found by Satyendra Bose. So, final conclusion of, well, not final conclusion of my talk, but final conclusion of Schrödinger after he had considered all these arguments. He said, the particles in the naive sense of the old days do not inherently exist. It's Schrödinger who said that. Okay? So, and it's interesting to see that not so many people are aware of that nowadays. Not so many, because, when you read popular science papers, you have the feeling that physicists are playing with particles, and you imagine that particles are little bodies that goes in a continuous trajectory as any body. It's not the case at all. When physicists say, I have discovered a new particle, that just means that he has discovered a new peak in energy somewhere in his accelerator, and he says, oh, that must belong to that type that I name a particle. But there is nothing permanent, continuous, and so on behind it. Okay, so the good theory to account for this strange non-individuality of so-called quantum particles, the good theory is called quantum field theory. And here you hear something new. Field. What is a field? We don't know what is a field, of course. But a field is defined as, a continuum of values that can be measured. For instance, when you say there is an electric field in this room, that means that if you come with a probe, you can measure a slight deviation of the probe. That's it. Okay. So, what is a field? Is a capacity to trigger a reaction in a probe. For instance, an electric probe or magnetic probe or something like that. Nothing more. A capacity, a disposition, a potentiality. Okay. Nothing. Here again, nothing inherently existent. Now, how do we conceive particles now in this new theory called quantum field theory? We conceive them just as levels of excitation of the field, nothing more. So there is nothing like, a little body that you can follow here and there. There is just an excitation of the field that triggers a reaction in the counter. And when a reaction is triggered in the counter, you say, oh, there is a particle here. But the particle is here again, nothing continuous, nothing individual, nothing intrinsic. There is a beautiful metaphor by Schrödinger already in 1925. He said particles are nothing but a foam crest on a fundamental radiation wave. A foam crest. And I must say, you know that Schrödinger was very much inspired by Indian thoughts, by the Advaita Vedanta and by Buddhism. So his metaphor of a crest on the wave, which is like, a wave on an ocean, is very similar to some metaphors of Advaita Vedanta about the mind. Another point that removes a little bit more of existence from these quantum particles. And this, I've expounded this to His Holiness in one of the Mind and Life conferences, and there was a long discussion about that. So here is the experiment. You have a cavity, a box that you have emptied of anything. You have emptied it from any gas molecule, and you have also emptied it from any photon, because you can do that by cooling the box, okay? And then you put a detector in it, in the box. If the detector is not moving, you detect, what do you detect in an empty box, by the way? You would say nothing. And indeed, you detect nothing when a detector is in an empty box. This is very intuitive, no problem. Then let's suppose that you give a kick to this counter, to this detector. You give a kick. You accelerate it. Then suddenly you see the counter in the empty box that counts plenty of clicks. Usually, when you hear a click from this detector, you say, oh, this is a particle. And here, in this case, you hear a lot of clicks, and you know that you have emptied the box before. So how is it? Okay, so that's the puzzle. It's called the paradox of Rindler-Quanta. What does it mean? It just means one thing. There is no way to say that particles exist in the absolute or do not exist in the absolute. The only thing we can say is that they exist, if even the word existence is adequate in this case, they exist relative to the state of the detector that is able to detect them. There is no point saying that something exists in the absolute. It exists relatively to the state of the detector. Then, knowing that, some physicists, such as Jean-Marc Lévy-Leblond, Bernard D'Espagna, and so on, have coined a beautiful expression, an expression that is also very appealing from a Buddhist point of view. They said, particles have the mode of existence of a rainbow. Why did they say that? So, particles do not have the mode of existence of grains of sand. They have the mode of existence of a rainbow. Why? Because a rainbow exists only in relations two eyes, yes, certainly two eyes, but also, you need at least three elements to have the phenomenon of a rainbow. You need light, a source of light, for instance the sun. You need droplets of water, such as when it rains, okay? And then you need an eye, or a camera, or anything, but I can tell you, do not have a rainbow without a standpoint from this which it is seen. If not, you may have, maybe if you can imagine photons everywhere, but this arc of colors come only if you have a standpoint, okay? Either an eye or a camera to capture the light in a point, okay? If not, you don't. So a rainbow is a phenomenon that comes in relation between three things, okay? Then, according to these physicists, particles are nothing more than something like a rainbow. They are phenomena, they are observed, but they are not something that you can catch, you can identify, just as much as you cannot catch a rainbow. You can see it, but you cannot catch it. Okay. Now let's come a little bit to, before I will come seriously to Buddhism, I wish to tell you something a little bit elaborate in philosophy of entities. This branch of philosophy that is concerned with the nature of entities is called, I hope you are not afraid by the word, it's called ontology, namely the discipline of beings. Okay. So let's take two objects. Here again, we start with very elementary cases, and then we come to more and more elaborate cases. Let's take two objects. They can be inherently discernible if they have distinct properties. Okay? This is the case of Leibniz. If they have a list of properties that is not identical to the list of property of the other thing, then we say there are two of them. But there is another case, much more interesting for quantum physics. It's the case in which things are not inherently discernible, but relatively discernible. Let's suppose you have two, I say A is at distance D from B. Being at a distance D is a relational property. And it's enough to say that there are two elements, because you cannot have, for instance, one element that is at distance D from itself. It would be absurd. The only possible distance of something with itself is zero, okay? Because it's the same. So if you have things that are at distance D from one another, you can say that they are distinct, that they are two, not one. Okay. Okay, and it's the case. It's the case precisely in quantum physics. In quantum physics, two electrons, I told you, have exactly the same properties. They have the same mass, the same charge, and moreover, due to the uncertainty principle, everything goes as if they had the same position, because their positions cannot be distinguished. Okay? So everything goes as if they had the same position. So if they have the same mass, the same charge, and the same position, are they the same or not? The answer is no. Why? Because they may have relations between them. For instance, we would say that two electrons, sorry, here I need a
Should I
third
hold it?
arm. Yes, yes. It's true that the gesture is important in this
Okay.
case. Yes, so there is a property of electrons called the spin, and it's represented by a vector. So an arrow pointing in a certain direction. So there are pairs of electrons that are such that they have opposite spins, such like that. You know that they have opposite spins, but you don't know which spin. You know that they can be this way, or this way, or this way, okay? But you don't know which case it is, okay? But just knowing that they have opposite spins is enough to distinguish them. Because, one electron cannot have an opposite spin to itself. It would be absurd. So if there are opposite spins, then there are two, not one. That's the point. So therefore, these electrons have no other criterion of existence than the relation they have to one another. That's the point. That's the important point. So much so that a physicist called David Mermin, very well-known specialist of solid-state physics, said, in quantum physics, relations have physical reality, but that which they relate do not. Relations have reality, what they relate do not. You start understanding what is happening. Okay. And here I want to allude to something that you were very well know, namely dependent arising. What is dependent arising exactly? Some people connect that with causality, but I think it's much deeper than mere causality. For instance, Nagarjuna criticizes causality if understood in the simple way, namely just productive causality. Something exists and it pushes something else that exists. It's not like that. It's more interesting and more subtle. For instance, let's read this sentence, this very famous sentence of Samyutta Nikaya. It's a sentence that defines dependent arising by a picture, a metaphor. And the example is two sheaves of reeds. It is just as if there stood two sheaves of reeds. Okay, this is one sheaf of reed, and this is another sheaf of reed. So if I were to pull towards me one of those sheaves, the other one would fall. If I were to pull the other sheaf of reeds, the other one, the first one would fall. So they are leaning to each other, and their stable position is only obtained by their mutual contact. So the property leaning against of these sheaves of reeds co-arises with that of the other sheaf of reeds. Okay? Leaning towards is a property that is relational. You do not lean towards if there is not something towards which you lean towards. And conversely, okay? So the co-arising is exactly that. It's complete reciprocity. It's complete relational definition of one by another. For instance, there are many Sanskrit words to make an equivalent of pratitya samutpada, namely dependent arising. Another word than pratitya samutpada is paratantra, which means woven of the other. Or paraparasiddha. I know I don't pronounce well, but paraparasiddha means established by one another. Okay? So it's the same thing for the quantum particle. They do not exist individually, separately, inherently, but in relation to the other. They are woven of the other. They have interbeing without having being. And this was something that it was became clearer and clearer in the 1990s. Now, beware. You have heard this sentence by David Mermin, I quoted earlier, that relations have an existence, but not the things that they relate. Does it mean that relations have inherent existence and not the things that they relate? Unfortunately, it's exactly what Mermin meant. Namely, he didn't take too much precautions and said that. He said, yes, relations have existence, real existence, inherent existence, you know. And 2 years after only, another physicist, Adán Cabello, a Spanish physicist, proved that even relations cannot have inherent existence. They have existence relative to, for instance, an experiment that brings out these relations. So even relations are relative. Even relations have no intrinsic existence. And I think this resembles a lot to what Nagarjuna said about emptiness, that even emptiness is empty. And here I quote, "From whomever emptiness is a view, that one has accomplished nothing." Okay? If you take emptiness as an entity, as something, and as a representation of something out there, then you have understood nothing. If you take emptiness as a view, you have not done completely your work, which is to deconstruct any view, to criticize any view, either the view V, or the view not V, or the view V and not V, or neither. Okay, this is a famous tetralemma. And here it is. We conclude with that, with the tetralemma, and with the fact that, maybe a short conclusion. Quantum physics sometimes is taken as a good analogy to several Buddhist views. But I think it should not be taken as an analogy of views. It should be taken as a good equivalent in terms of the criticism of views. Quantum physics is a beautiful Madhyamaka exercise. It is not a picture of something. I think I will stop there and wait for your questions.
Thank you.
Whatever knowledge or perception we have about the reality of any object or any phenomenon, that knowledge or perception is basically subjective. Is there any way to know about an object from objective side?
What is objectivity? When do we say that we have obtained an objective knowledge? When we have elaborated a formalism or a set of sentences that everyone can check and accept. So, in fact, what we call objectivity is universal acceptance by subjects.
Intersubjectivity.
Intersubjectivity.
In objectivity also there is a subjectivity. Let me explain.
Exactly.
No, intersubjectivity.
Yes.
Let me explain you.
Yes, yes.
Supposingly if we take any object, say supposingly this is black.
Yes.
It may appear to you black.
Yeah.
If I ask another person what is the color of this,
Yes.
he or she will also answer it is black.
Yes.
But his perception and my perception may be different.
Yes.
But both are saying black because
Yeah.
right from the beginning we have been taught that whatever you perceive, that color is black.
Absolutely.
It means there is a scope of subjectivity even in so-called objectivity.
Absolutely.
So my question is how exactly we can confirm that whatever knowledge or perception we have about the reality, that reality is an objective reality.
We can't. The answer is that we can't. We can only use this kind of method. namely trying to find a set of criteria that enable us to agree. But more than that, we cannot. And yeah. So, and it's exactly what we do in mathematics. What is, for instance, when you have a theorem, when is the theorem valid? When it follows certain rules that everybody can follow and confirm that if you have learned correctly mathematics, then you will land into this conclusion. That's it. What more? Yes.
What the Frankenstein said, like, it is not whether ghosts exist or not, but when I say like ghosts, when I say ghosts, you understand it.
Yes.
Sometimes it seems like, and you say an atheist, sometimes it's become like a Christian atheist or Muslim atheist. Like, it becomes very like relatives, like whether you get it or not. Like, when you say like I'm atheist, so I'm atheist as a Christian atheist or like a Muslim atheist or something like that. It's very relational, like.
I don't know what to answer to this
He
one.
was talking about ghosts.
Ghosts, yes,
It's like, it was
ghosts.
another argument. Like Frankenstein said, it is not whether ghosts exist or not. When I say ghost, you understand it.
Yeah, of course. Yeah, of course. The mode of existence of objects are many, and one of the modes of existence is called fictional objects. Namely, everyone understands the word ghost because we have defined the word ghost before in many novels, in many stories, and so on and so on. So people understand the meaning of ghost. The point is that did they see ghosts? That's the only.
It's very relational. Like it's related to what you said.
Exactly. Yeah. But one criterion of existence, the final criterion of existence, well, it's not the final. It's just a minimal one. It's to be perceived. But it's not enough. Perception is essential, but it's not enough. Okay? Because you can perceive a click, a spot, and what does exist in that case? But when there is no perception, no possible perception, then difficult to tell that it exists. Or at least it exists in another mode, for instance, the mode of fictional objects, like ghosts. Yes?
Just one thing, what are your thoughts about energy as a form of existence? Because you've been talking about particulate natures.
Yeah.
But energy is not a particle or matter. So
True. Yeah, good question. So energy sometimes is a little bit reified, as you know. We know. For instance, at the end of the 19th century, some physicists have been called energetists. And they said the only thing that exists is energy. But here again, when someone says something about stuff, we have to inquire into what are his or her reasons. How does he or she knows that? And this is the crucial point. So why did these persons say that only energy exists? It's because in the 19th century, there were two new theories that came side by side to the former physical theory that was called mechanics. Mechanics was founded by Newton, Galileo, and so on, and it was the science of the motion of bodies. But then there were two other sciences, the science of thermodynamics, the science of heat, and the other science was electromagnetism. So the science of electrical and magnetic effects. The point is that there was only one common point that one could establish between these three theories. It was a parameter called energy. You could transform the energy of heat into energy of motion, and you can transform energy of motion into energy of waves, electromagnetic waves, and so on and so on. Okay? Okay, but what was energy at that time? Only a quantity that can be transformed from one form to another. Some people at that time said, what is energy after all? It's the power to transform things, just the power. It's not a stuff, it's a power. The power to transform, for instance, a power to get something hotter, or a power to move something, to push something, okay? So, is it a stuff or not? No, that's very difficult. Nowadays we are at the same point, because energy, for instance, the new thing since Einstein in 1905 is that energy can be transformed into matter. Okay, so there is it becomes clear that matter and energy are two forms of what we don't know. But even asking the question, the form of what, means that we think very Westernly that there must be some stuff underlying, you know. And here again, it's a problem. So, yeah, we have a science of transformation, but not a science of stuffs. That's the point. A science of impermanence, not a science of permanent things. Yes.
If I understood you correctly, you said that, you might clarify that again, that quantum physics is a form of criticism.
Yeah, well, it would be nice if it were all that.
Yeah, and that leads me to next. So would you say that a positivist approach to science, or always looking for proof, is actually becoming outdated?
No, it's not outdated, because the positivist view of science has one quality. It is very low in interpretation. It doesn't make too much, fuss about views, about representations, and so on. So it's sort of positivism is a sort of therapy. It levels all ideas, and it forces you to think in the way I tried to illustrate, namely, okay, you say that there are particles, but what are your proofs? On which criterion do you base your assertion that there are particles? And when you see the criteria, you see that so many are missing that you cannot really speak of the existence, especially the intrinsic existence of particles. You see. So when I cannot say quantum physics is a form of criticism. I just say that quantum physics has put such pressure on common views of the world, namely essentially Western views of the world, in terms of substances and properties, that it pushes people towards very critical attitudes. And tomorrow I will expound one of these new views of quantum physics at the
IIT tomorrow.
IIT.
What time?
At 10. And so it's a new view of quantum physics, in which quantum physics says it's really a theory with no view at all about the world. It's a view about our position of the world. It's a completely conventional form of truth, a practical form of truth that enables us to anticipate events and to act. Action and anticipation, which are always connected. So, and this no view of the world that is supposed to be quantum physics is nevertheless very interesting, because it has this very Madhyamaka flavor in it, and it can make you imagine, for instance, some people have imagined what can be the world in order for it to prohibit any representation or view of it. So it's sort of a meta view, you know. Yes, I think it's you.
Professor, you might have
Yes.
you might have mentioned or concluding particle having ultimately one property, that is spin, which determines its identity, might have in terms of quantum physics.
Yeah, it's
But-
not.
but-
It's, yeah,
But there's one particle called Higgs boson, which doesn't seem to have a spin. So-
Yeah, no, boson have spin. They can have spin 1, but the fermion have half spins. Instead, the bosons usually have integer spins. Okay. For instance, yeah. But boson is another case. It's not a case of relative identity. It's a case also only of numerical non-identity. Okay, I didn't speak of bosons on the last slide. I could not explain everything, so I took the case of fermions because it was more illustrative of what I wanted to say. Okay. Yes.
If there is no view, how do they attribute to the functionality of the relative world?
How do they?
How do they attribute
Yes.
to the functionality of the relative world?
To the functionality of
Yeah.
the relative
If
world.
there is no view,
Yeah.
yeah. It's almost like saying that
Yeah.
there is no view that I'm listening, or you're talking,
Yeah.
or the water is moving, or the air is moving.
Yeah.
So how do they really put that perspective? I mean, this world is really working
It works.
at the relative level, at the functional level.
Yeah, exactly. Yeah.
So how do I say, if there's no view,
Yes.
that this world is functioning?
I don't know if this world is functioning, but the system.
No, that's right. That's why I said the relative world,
Yes.
not the ultimate world, the relative world.
No. I understand now your question, but it's not. I would not say the world is functioning, but we can make the world function if we act properly, and it's exactly what the new interpretations of quantum physics try to convey. The idea that it's not the world in itself that works. It's our relation with the world that can be made to work, which is quite different.
No, when we say it's a working,
Yes.
the relational part is already inbuilt in that.
Yes, but
Yeah.
then you take a meta view.
As you are speaking, I'm listening.
Yeah.
There's a functioning going on in your
Yeah.
mind, in my
Yeah.
mind, so there's a kind of
Yeah,
relationship.
but you need then
So-
a third point of view, the point of view of someone who listens at both of us and say, oh, this couple of people functions because they are dialoguing,
Mhm.
So, but it cannot be that it's completely independent of any possibility of representing the relation.
Yeah,
So-
so isn't it that view that the third person is saying that
Exactly.
we are interacting, we are talking?
Mm.
So there's a view.
It's a view, but it's not a, it's not a view in an absolute sense, because
Yeah.
here again, you can have a fourth and fifth and so on people who take a glimpse on this relation and have a relation with the set that is, as you said, functioning.
Mhm.
So you cannot say that there is a view in the absolute. There is a view for each one of us within the process of relating with each other. But this view is not an absolute view, it's a relative.
Yeah, that's it. That's it.
That's fine.
Thank you for your talk, Michel. I haven't engaged with QFT, but the word field.
Field.
Right, raises certain questions. If you look at the ontological and the semantic dimension at the same time, what quantum field theory would suggest is that it's ontologically empty, given the madhyamic flavor,
Mhm.
but semantically we can use field
Yeah,
as a better concept to work
exactly.
out the relations in language.
Mhm, mhm.
To say something like that of QFT would not be incorrect, right?
Yeah. Look, it's interesting because there are two, well, apparently it's the same thing, field and quantum field, but in fact it's not. What is a field in classical physics? A field is the capacity for a certain portion of space of triggering a modification in the probe. Okay? But you can treat this capacity of triggering a reaction in the probe as if it were continuously evolving even when you don't put the probe. That's typically classical. Okay? There is no contradiction if you say that this set of dispositions evolves spontaneously by itself even when you don't put a probe. Okay? Now, in quantum physics, it's not the case. A quantum field is not the same type of entity as a field, because saying that it evolves inherently without, even when it's not in relation with a probe, lands into contradictions. So it's completely different. So in one case, the value of a field is called a property of a field for that reason, because it's proper to it. Instead, in the quantum field, it's only called an observable, namely something that is not proper to it, but it's relative to the act of observing it. So the field and quantum field are different. Field is a disposition, and a quantum field is a disposition to have a disposition, which is even more eerie, I would say, or I don't know which word I would. A little bit weird. Yes, it's weird. Yes.
Professor, thanks for coming. You had mentioned during the course of your lecture there are no particles in quantum physics. Could you just explain in 5 sentences?
Yes.
5 sentences. Why not 10?
There are no particles. That means that there are no such thing as what we usually take as particles, namely a little body which has a continuous identity, continuous existence, and so on. But there are phenomena that in certain circumstances we can gather together and have a little bit something similar to what we think are particles in everyday life. You know? So it's really much less than our ordinary life conception of particles. It's just a set of appearances.
See, the protons, bosons,
Yes.
neutrons, atoms, etc., 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 etc.
Yeah.
So, could
Yeah.
you classify?
Yeah. Here is also, when you open a textbook of physics, you find such words, proton, neutrons, electrons, and so on. But interestingly, they are usually used in the plural, namely that they denote a species, not a set of individuals. Okay? So it's very interesting. That means that the individual being in that case is not the constituent of the species. It's rather the other way around. It is the species that is defined, for instance, by a set of values, mass, charge, and so on, and it is instantiated by some spots that you see in screens or in detectors, and you say, this is one electron. But it's not one individual, intrinsically existent electron. It's just a spot that illustrates the species or the set or the class of electron. So it's many things that the problem is language. Clearly.
Yeah, that's correct. If you would have seen Steven Spielberg's movie Indiana Jones series, in that the spacecraft, the aliens go and then there's a skull in the Incas Mayan mountains in South America. There's a spaceship and it goes away into the sky. So the old man who found the skull, he says maybe they were looking for spaces in between.
Yes, I see.
You see?
Yes, okay.
So they are such an advanced state of civilization that they can come and go as they please.
Yeah.
To Earth.
Yes, it's an interesting illustration. Thank you. Yes.
If quantum physics is an issue of concern of language, how does it relate to semiotics?
unfortunately, not the physicists don't pay enough attention to the way they explain their discoveries, because if they attention, they would not trigger so much misunderstandings. So, for instance, if they didn't use substantives to name, for instance, protons, electrons, and so on, they would not trigger the thought in, the lay people that there are substances, little things existing. So clearly, the fact that we use such words makes lead us completely astray. So if some serious work in the semantics of the sentences used by scientists were done, then maybe less misunderstandings would be triggered. By the way, just a quote by Einstein to illustrate this. Einstein said once, if you want to understand science, please don't listen or read what scientists say about science. Just look at what they are doing. Okay? So their language is not completely adequate to the complexity and subtlety of what they are doing. So that's the reason why here I could have also entered into mathematics, but it's not the only point. I entered into the detail of the experimental criteria they used. So I entered into how scientists act in their laboratories, not only what they say about their discoveries.
Michel, I was interested to know, in quantum physics, how do you understand the point when quantitative change becomes qualitative change?
Yeah.
Or the relationship between, cause and effect?
Yes. For instance, I'm trying to find an example.
Okay.
To answer your. For instance, you know that according to the amount of energy that you use in a collider, you trigger what is called the creation of a certain number of particles. So, my teacher of physics and philosophy of physics, Bernard D'Espagna, used to say that quantum physics is this, and also relativistic physics, is this extraordinary discipline in which you can transform properties, namely qualities, into quantities.
I see. The other way.
Exactly. So, for instance, you transform a property. Say, the energy of a particle is a property of a particle in the usual sense. But then you make the two particles with a certain amount of energy collide, and then they become new particles. So the properties of the particles have become particles. So there is a transformation between the concept of property and the concept of thing. Mm-hmm. But of course, this is possible only because particles are not something inherently existent. Okay? It's not magic. It can be understood if we understand that particles are not something so different from energy, precisely.
Cause and effect?
Cause and effect, yes. There are many things to be said about cause and effect.
Is it monocausality, multi-causality,
Yeah, absolutely. The first thing that was said by the creators of quantum mechanics was that the principle of causality was in jeopardy due to quantum physics, because they said we cannot predict something. We cannot predict a single event. There is indeterminacy. uncertainty, like in Heisenberg's principle, or in the formalism of quantum physics, what is the famous function psi that is ruled by the Schrödinger equation? It is just a mean to calculate probabilities. So you don't have anything determinate in quantum physics, except for the law that rules the probabilities, nothing more. So apparently you have a loss of causality in quantum physics. And I remember His Holiness was very upset by that.
Because you have karma in Buddhism.
Exactly.
Yeah.
Of course, you could say, okay, it acts at a different scale. Karma must act at a higher scale than the little electrons. But yet, there is a way to save causality in quantum physics. If you accept that causality, here again, is not absolute but relative. Namely, when you say that one event cannot be predicted, and therefore it looks like there is no cause to this event, okay, it's fine, but you forget something, is that in order to trigger this event, you have made an intervention. You have done an experiment, and this event has been triggered by the relation between your experiment and what you want to explore. So, even though there is no absolute causality, there might be relative causality. And this is even the object of a certain theorem by some physicists. So, I think this is very, very congenial to Nagarjuna's adoption of dependent arising, but criticism of intrinsic causality in some of his character. So I answered that to His Holiness.
I see that.
And he said, that's fine, that's it.
I see.
Yes.
Thank you.
Yes.
Could you recommend some books to start with in quantum physics?
Which book to start with in the...
Some few books that you could recommend us.
But at which level?
To start off.
Yeah, but do you know some mathematics?
Oh yeah, I do. I have
okay.
some ideas about the Heisenberg's uncertainty principle, about the Schrodinger's cat.
So you have...
yeah, I have some basic physics experience.
Okay, good. Then you can try the book by Leonard Susskind, which is... I don't remember its title, but the title must be something like some elements of physics or some elements of...
Could you spell the name of the...
Susskind. S-U-S-S-K-I-N-D. Leonard Susskind. There is a series of books of introduction to physics. One is an introduction to classical physics, another one is introduction to field theory and relativity, and another one introduction to quantum physics. I think all these books are remarkable because they are clear, simple, and yet not just words, you know. So if you can read a little bit of mathematics, I recommend this one. If you can read more mathematics, I can recommend other.
Yeah, please go ahead.
Well, the Bible of quantum physics is the book written by a French author, but it's popular everywhere in the world. It's called, or the Bhagavad Gita maybe of quantum physics.
Yeah.
Sorry, it's called the author is called Cohen Tanuji.
You have to spell it.
Cohen, C-O-H-E-N.
Cohen.
Yes. Tanuji, T-A-N-N-J-I. And two other authors also. Cohen Tanuji and two other authors. It's just called Quantum Mechanics 1, 2, and 3. It has been translated into English, and it's a remarkable book because it introduces even the mathematics, if you have enough mathematics behind. But even the mathematics of the theory is in the book, and then you have plenty of exercises, plenty of training of. So it's really. I learned quantum mechanics by this book, by the way.
So also, what is the difference between? I know quantum mechanics is the subset of quantum physics, right?
Yes, please repeat.
So what is the difference between quantum mechanics and quantum physics?
Quantum mechanics is the first state of the theory. It's a quantum theory of motion.
Right.
Okay.
It's the mechanics, right?
Mechanics.
Yeah.
Quantum physics is more general. Yeah. It includes quantum field theory, quantum chromodynamics, whatever. So quantum physics is the generic word. Quantum mechanics is the first initial theory that was created in 1926. A physicist.
I know.
Oh no, I'm not a physicist, but I've studied some physics and maths.
Yeah.
Any other? That's it?
All there is.
Yes, Kabir? A bit louder.
Madhyamaka speaks of things existing merely by name.
Yeah.
By name.
Yeah.
Does that apply in any real sense to what you've been speaking about, quantum theory? Do things just because
names.
we've designated them?
Um,
Otherwise it's kind of inexpressible, but there's a name, so yeah.
Yes.
The observer is getting a name, a designation, so therefore something exists, which is indefinable.
Well, the name is important in what I've said, but it's probably not the only thing. It's a way, the name crystallizes, for instance, a set of phenomena. The phenomenon of a spot on a screen, then the phenomenon of measuring the mass, then which is done in a certain way with certain instruments, then the phenomenon of measuring the charge, which is done with other instruments. And then you gather all these phenomena with a name, electron. So the entity, to a certain extent, you could say that the entity exists by its name, but it's not a completely arbitrary name. It's a name that crystallizes a coherent set of properties, I would say. Or not properties. Here again, I am guilty of using this word property. I should say a coherent set of phenomena that are triggered by a coherent set of experimental actions. So you could say that the name crystallizes a network of dependently arising phenomena. Okay, that's the idea.